Hello, and welcome to the AI Research Roundup. I am Alex, and today is May 14th, 2025. We're looking at a paper from Hugging Face's trending list, published 2 days ago, titled MiniMax-Speech, Intrinsic Zero-Shot Text-to-Speech with a Learnable Speaker Encoder. This research paper introduces an auto-regressive text-to-speech model, meaning it generates speech step by step for high-quality output. Its core innovation is a learnable speaker encoder, a component trained to extract a voice's unique quality, its timbre, from untranscribed audio. This enables zero-shot voice cloning, creating speech in a new voice from a short sample. It also uses a Flow-VAE, a special module enhancing audio representation for better quality. Alright, so this first figure gives us a nice overview of the MiniMax-Speech architecture. We see that the system takes in raw audio, which feeds into that learnable speaker encoder we talked about, to capture the voice's unique characteristics. Simultaneously, text input goes into an autoregressive transformer. This transformer then works with the speaker information. Next, a flow matching stage, which is a technique to precisely align the generated audio features with real audio characteristics, refines this. Finally, the Flow-VAE decoder, using that special module for enhanced audio representation, generates the high-quality speech output. Okay, so this figure gives us a closer look at the proposed latent flow matching architecture. Part A details the Flow-VAE model. An encoder first extracts continuous speech features, which are like detailed numerical sound descriptors, from the input audio. A decoder then reconstructs the waveform. Importantly, a flow component converts these features to a standard normal distribution, a specific statistical pattern, using KL divergence, which measures how different two distributions are. Part B then shows the flow matching model itself. This generates those target speech features by conditioning on the autoregressive transformer's output and speaker characteristics, refining them along a probabilistic density path. Moving to the results. This table compares MiniMax-Speech with other models on voice cloning tasks in Chinese and English. We see metrics like word error rate, or WER, which tells us how accurately the synthesized speech is transcribed, so a lower score is better, and speaker similarity, or SIM, which measures how closely the generated voice matches the target speaker, so here, a higher score is better. For Chinese, in zero-shot cloning, MiniMax-Speech achieves the best word error rate at 0.83 and strong speaker similarity, really showcasing the impact of its innovative design. Building on those objective metrics, this next figure presents the Artificial Analysis Speech Arena Leaderboard. This is a ranking based on human listeners, judging qualities like naturalness and expressiveness. And look, MiniMax-Speech O2 HD is right at the top with an Arena ELO score of 1153. Arena ELO is a rating system where higher scores mean better perceived quality by people. The 95% confidence interval shown next to it that indicates the statistical range and reliability of this ELO score. This top ranking by human evaluators really underscores the model's strong performance. Alright, to understand what makes MiniMax-Speech perform so well, this table presents an ablation study on speaker conditioning methods. An ablation study is a type of experiment where researchers systematically remove or alter parts of their model to see how each component affects the overall performance. Here, we see different methods like using their proposed learnable speaker encoder versus other approaches like SPK embed or only prompt. The learnable speaker encoder consistently shows strong word error rate and speaker similarity, particularly in zero-shot cloning, which really highlights its effectiveness in capturing speaker characteristics without prior training on that specific voice. Following up on how different components contribute, this table now isolates the impact of the Flow-VAE. A variational autoencoder, or VAE, is a type of neural network architecture that is particularly good at learning efficient, compressed representations of complex data, like audio features. The Flow-VAE is an enhanced version. We are looking at models with the standard variational autoencoder versus those with the Flow-VAE across zero-shot and one-shot tasks for Chinese and English, using word error rate and speaker similarity. The data shows that incorporating the Flow-VAE generally leads to improvements. For instance, in zero-shot scenarios for both languages, the Flow-VAE model scores better on both metrics, underscoring its positive impact. So, to conclude our look at MiniMax-Speech, it is evident that its core innovations, the Learnable speaker encoder and the advanced flow variational autoencoder, are central to its success. This model delivers truly high-quality, expressive speech and stands out for its robust zero-shot voice cloning, that is, creating a voice from just a short audio sample without needing any text transcription. This capability, along with strong multilingual performance, really makes it a state-of-the-art solution. That is all for this AI Research Roundup. Thanks for listening.